this video, we'll discuss the problem will and con. So, in this problem, what it is given is that there are some minions, okay, so which are elitist in nature. So, it is given that if minion X admires minion Y, okay, then Y thinks too highly of himself and does not admires Y back. So first let's read this whole statement, then we will understand all the points which are given to us in the problem statement. Also, if X admires Y, X also admires everyone that Y admires. So these are the 2 points which is written. The first is that if X admires Y, it is not necessary that it does back admires X. And the second thing is that if X admires Y, it also admires everyone that Y admires. Fine. Now, all the minions are going to present in the villain con. They wanted to make sure that they do not dress up in the same color as someone who admires them. So they want that if someone admires them, so the color of their dress should be different. They should not be of the same color. There are n minions and m relations given to us. This is also given to us. The relations are given in a 2D array. Each relation is in the x1 and y1 format, which means y1 admires x1. We have to find a minimum number of different colors that minions will be dressing up. This is what we have to find. For example, if we consider this particular case, you can see there are 6 relations given to us and there are 5 minions and 3 different colors are required. Now we will understand how these 3 different colors are required. So what we will do, we will consider this particular test case which is given to us, okay, and we will try to understand how can we find minimum different colors which are required. Okay, so this is what we have to find. So first let's consider the test case which is given to us, and we will understand this. So this is the test case, the first test case which is given to us. So according to this, we have a matrix of size 6 which contains pairs basically, and a pair x, y denotes, which is given to us also in the problem statement. It is saying us that if there is a pair x, y present, it means y admires x. Sorry, yeah, y admires x. Fine. Or let's once again let's check the problem statement so that there should not be any confusion. Yeah, it means y admires x. Fine. So this is given. So now let's see that how can we write it. If it is written that y admires x, so can we write it like that xy, or we can write it like yx, means y admires x. This is how we can write y admires x. This is just like a directed graph, you can see. It is just like a directed graph. These are the 2 nodes and this is the x, which is telling us that yeah, y is admiring x. So this is how we can represent our problem statement. So now let's first plot all the relations which are given to us. Let's try to plot it. Okay. So we will plot all the 6 relations which are given to us in this particular test case. Let's see how can we do it. Okay. So see here what it is given to us. First is 1 3, means 3 admires 1. We can write it like this: 3 admires 1. Now 2 3 means 3 admires 2 also, so we can write 3 admires 2. Now 3 4 means 4 admires 3. 4 admires 3, so we can write 4 admires 3. Now also there was 2 points. The first point was that if x is admiring y, doesn't mean that y is also admiring x. It doesn't mean necessarily. This was the first point given to us. And the second point which was given to us was if x is admiring y and if y is admiring z, then x is also admiring z. This was also given to us. These were the 2 points which were given to us in the problem statement. The third point was that there should be different colors of everyone who is admiring each other. There should be the color of their dress should be different. So those were the 3 points. Different colors. Okay. this particular property that if x is admiring y, y is admiring z, so x is also admiring z. And the third thing is that if x is admiring y, then it is not necessary that y is also admiring x. It is not necessary. These were the three properties which are given to us in the problem statement. Fine. So now we will understand that how can we use these three properties to find our answer, that how many different colors are required. So you can see here that if this 4 is admiring 3 and this 3 is admiring 1, so obviously this 4 should also admire 1. But that is always given to us in the test case also. So the test case are also good according to us. You can see here there is a relation given to us that 4 is admiring 1. It is already given. And it is also proved, we can also prove it by the condition given to us. That if 4 is admiring 3, 3 is admiring 1, so obviously 4 should admire 1. Okay, fine. Now next, one more thing. 5 is admiring 2. Okay, so I can write 5 here, which will admire 2. Okay, now 3 is admiring 5, means 5 is admiring 3 basically. 5 is admiring 3. We can write here like. So this is the basically the graph, the final graph which is given to us. We can easily form this particular directed graph using adjacency matrix. We will understand, we will code how can we implement this. This is the graph. Now the thing is, how can we find minimum different colors required? That is the thing which we have to find. So now let's understand this one, that how can we find it. So obviously, for example, let's take the example here that if the color of this, so if the color of this 4 is, for example, A. Let's take A as a color. So the color of this 3 should not be A, and also the color of this 1 should also not be A, because there is a probability given to us. Let's move towards the problem statement once again. Here you can see that they want to make sure that they do not dress in the same color as someone who admires them. So if, because 4 is admiring 3 and 4 is also admiring 1, you can see here 4 is admiring 3, 4 is also admiring 1. So if the color of 4 is A, so 3 and 1 should not be of A color. It should be of different color. So yeah. So we have taken the color of 4 as A. So now let's talk about the color of 3. So obviously it should not be same as of 4. That is what given. So let's say that the color of 3 is B. So now this A is of color, 4 is of color A, 3 is of color B. Fine. Now if we talk about this 1, because 3 admires 1 and 4 also admires 1, it means the color of 1 should not be A and should not be B. It should be different. So let's take the color of 1 is C. So we have given colors to these 3. Now if we talk about the color of 5, we can use A here. Why? Because we can use it. It is like that 5 is admiring 3 and 3 is having color B. So we cannot give color B to 5 because 5 is admiring 3. Also we cannot give color C to 5 because if 5 is admiring 3, so it is also admiring 1. So we can give it a different color. So instead of taking a third color, we can use A only, na? Because between 5 and 4 there is no relation. So we can use A here. Similarly for this 2, we can use C. Why C? Because yeah, there is a relation between 5 and 2. 5 is admiring 2. There is a relation between 3 and 2. 3 is admiring 2. But there is no relation between 1 and 2. So if the color of 1 is C, so we can also take the color of 2 as C. So we have taken 3 different colors A, B and C for our test case. This is what given to us. You can also see the answer of this particular test case. It is 3. It is given to us. This 3 here. So this is how we can do. So obviously what we have to find the longest chain which is given to us. What? The longest chain of minions which is given to us. Because in each chain the number of colors should be different. Because if this is a chain, you can point out that this is a particular chain. This from 4 to 1. This is a chain. This is another chain from 5 to 3 to 2, or from 5 to 3 to 1. This is another chain from 5 to 2. Okay, so these are some chains in this particular graph. So if we take the longest chain, so it will tell us that how many different colors are required, because no more than color will be required. Okay, but the thing is, how can we find it? So we can easily use traversing technique to traverse through each, and what we will do, we will traverse through each and every node, and then we will check that what is the longest chain possible from a particular node. Because if we are starting from 4, you can see that from 4 to 3 to 1, this is the longest chain of size 3, or you can say 4 to 3 to 2. This can also be the longest chain, and then we can output that 3 different colors are required. This is how we can do it. So now let's move towards the code part, and let's see how can we code it. Okay, yeah. So here we are provided with a matrix mat, which will give us the relation between the minions. N are the number of minions and M are the number of relations, which is given to us. Now what we will do, first of all, we will create a graph. We will create a graph with the help of this matrix, okay, which is given to us. So let's name that graph A. Okay, so we will name that graph A, and it will be one bias, so I am taking up to n plus 1. Okay, now what we will do, we will iterate through this matrix mat which is given to us. Okay, yeah, fine. Now what we will do, we will create the graph. Okay, so for that, what we will do, what we have to do, it is showing us that y is admiring x, so we will push back y in the index of x. This is how we will create the graph. Okay, so if we store both the values in the pair matrix, because this is a pair matrix, so we can write it like this, that x is basically the value and y, because x comma y was the pair which we have discussed. It means that y admires x. It means like this. Okay, now we have pushed back the value of y in the, this is just like a adjacent line. Okay, now next thing what we can do, we have to calculate that the longest chain. So for that, what we can do, we can take another function, because we have to call recursively for each and every node. Okay, so we will form another function. Also, what we will take a third array. That array will basically contain that how many nodes are followed by a given node. For example, if I store for this particular, if I check for this particular case only, which is given to us, which we have discussed, let's take array D. Okay, let's take array D. So this D array will contain the length. Basically, this D array will contain length after every node. So if I talk about D1, so this D1 will contain just 0, because there is nothing after. We can write it like 0. Okay, or if we make it like 1 only, because yeah, there is a 1 present, so we can make it like 1 also. Fine, but at initial we will initialize it by 0. Fine? Yeah. Now if we talk about D3, it will contain 2, because after 3 there is a 1. And how can we calculate that? Or we can say it like, if I store here 1. Yeah. So how can you do it? Here is a 1. So what I am telling you is that when we will check for this D3, we will check for its child. And here in this case, the child of 3 is 1. So because the distance, or we can say the value of this matrix for this 1 is 1, obviously, so the value for this matrix D3 will be 1 plus 1. because we have added a 3 node also here. Similarly, for this 4, we will check for its child, which is 3, and we will increment one more. So for D4, it will be 3. So you can see here that for the longest chain here is 3. Similarly, for 5, it will check for 3 because 3 is one over child of 5, and it will check for 2 also. For 2, the value will be 1, and for 3, the value is 2. You can see here. So it will take the maximum value, and it will take store 3 here because 2 plus 1 is 3, and this is the longest chain. This is the longest chain instead of this one. This is what we will not take. So this is how we can calculate. Okay. Yeah. So now let's again move towards the code part. So for that, let's also take another array, D array. So what we will do, we don't know the basically size of, or because we are initializing that D array outside our scope, outside our function. So what we will take, we will take the size of that D array as the equal to the maximum size which is possible in this particular problem. Okay, if you see the constant here, it is just 10 to the power 5, the value of n. So we can take it up to the maximum one, the maximum value of n which we can take. Now what we can do, we can initialize a function. Okay, so let's take name the function f. Okay, so let's name the function f, and it is basically dfs. Okay, which we will do. So that function will take I is the current node from where we will check. A is the matrix which we have declared here, and one more matrix which is visited matrix, which is used in the case of DFS. So what we will do, we will also initialize a visited matrix, okay, which will make record of the nodes which we have visited. Okay, that's the simple thing. Fine. Now what we will do, now we will first place a base condition. So what is the base condition? So if I write the base condition here, so it will be simple that if we have already visited to that particular node, means we have already calculated the value of di for that particular node, that how many, what is the maximum longest chain after that node. So we have to just return that, the value of di, if we have already calculated. But if we have not calculated, then we will check it. So first of all, what we will do, first of all, we will make the visited of that particular node is equal to 1. Means, yeah, now we have visited. If we have not visited in the past, now we have visited. Now we will take a counter, let's take C, which will basically store the length, okay, the longest chain length, the length of the longest chain. Fine. Now what we will do, as discussed, we will traverse, or we will check for each and every child for our current node I. We will check for each and every child. So for that we will use a for loop. Okay, and in that we will take let's take a variable child. Okay, iterative child, which will iterate through all the child of AI, means ith node. Okay, now we'll check for the same condition for child also, the same condition, that if we have already visited child, in that case, what we will do? In that case, we will update the value of C, because C will be obviously the max of C, comma 1 plus the distance of child, as we have discussed. As I've discussed here, na. If I move towards the statement once again, you can see here that we have discussed the same thing. For example, here, just a minute. Here, what I have discussed was that the length for this 3 was the length for this 3 was 2, this, and the length for this 2 was 1, because only this 2 is present. So this 5 will check for both this 3 also, this 1 also, and it will take the maximum of this, which is 2. So it will store 2 plus 1 is equal to 3, means this particular length instead of this. This is what we will do. Okay, this is what we are doing. Okay, we are trying to implement. Now, if it is not visited, in that case we will recursively call the function again to count the value of, to calculate the value of that particular d child. So we will use the function again to compute the value of this d child recursively. Okay, and after, when we will calculate the value of C, we will assign the value to di, which we have calculated, and then we will simply return di. Okay, Now we have implemented this particular function f. So now obviously, as we have discussed, we have to check for each and every node, or we can say minions. We will start from 1, go up to 10 n. So because it is 1 bias, we can take from 1 also. And let's take a variable answer, which will store our answer. Okay, so this answer will be basically max of answer comma. Now we will call our function. Okay, so our function will take f, our current node I, our adjacency matrix, and our visitor. Right. So this will give us our answer. And also this answer, we will not return the answer. We will return answer plus 1. Because according to our logic, you can see that it is just adding the value of child. So the value for the last child will be 0 only. The value for the last child will be 0 only in our case. You can see here. If I discuss the value for this last child here, which is you can say 2 and 1 in this case, like this, 2 and 1. So it will be 0 only at the start. So obviously we have to add we have to increment it by 1. Okay, so according to the logic, the value of this 5 will be 2 only. The value of this 3 will be 1 only. So we have to increment 1. You can dry run it to understand it more clearly. Okay, so now we have returned here. So this is what we have got. Okay, so this is how we have implemented the thing which we have taught. So we have first taken a visited matrix, we have taken an adjacency matrix, we have created it, we have created a graph, and then we have done all the things. So now the time to compile our code, and let's check it for the time for sample test cases. So yeah, this compiled successfully. Now let's submit it. Yeah, fine. So it is compiled successfully. So now if we talk about the time complexity and space complexity for this particular solution. So first let's think about the space. How many space we have required. Okay, so we have created an adjacency matrix which was of length n, a visited matrix of length n. Okay, so we have created 2 matrices of length n, and we have not taken any other. So obviously the time complexity for this particular algorithm is O(n). Sorry, the space complexity. Okay, the space complexity for this particular is O of n. This is the space complexity. Okay, because we have just used. But yeah, there is one more thing. In that adjacency matrix, we have pushed back the value of y. So it is not of just O(n). If we talk about, it is not of O(n). That is what we have to understand. We have taken a just a minute, vector int a, and this is what we have taken. So the size of this array was n plus 1, but here we have to also push back some other nodes. So the overall, and there are basically m relations, so there should be m things here. So the overall time complexity will be O of n plus. This is the overall time complexity, and space complexity. Space complexity. I'm just missing it out. It is space complexity. Okay, and if I talk about the time complexity, so what we have done, we have recursively called the function. Okay, we have created a function, we have recursively called it for each and every node, and then for each and every node we have, and for each node we have called for each and every child of that particular node. So the time complexity will be also O of n plus 1. Okay, so this is the time complexity and space complexity for the solution which is given. I hope you got the video. If you have any doubt, you can comment it down. Also, you can share this video with your friends. Please like the video, subscribe to the channel, and keep solving on code courses. Keep practicing.